Okay, so in this video, I'm going to be talking about horizontally launched projectiles. First thing we're going to do is we're just going to try to understand the projectiles. For example, if we have a baseball being dropped off a cliff and a cannonball being launched off a cliff, what kind of motion do these two things have in common? Okay, one, they are both projectiles. Okay, even though this one is only falling down while this one will go in a curved path, both of them are under the influence of gravity alone. Gravity is going to be the only thing accelerating both of these objects. Therefore, they're going to fall down at the same rate. The only difference is this one will be falling straight down, where the cannonball will be moving over as it falls down. Okay? So using that knowledge, we can figure out where the ball will be at any time for both of them. So let's start down here with the baseball. For the baseball, if we want to know where it's going to be at time 0, well, it's at the top. Well, that's 0. Okay. So if we want to find the delta y, we're going to use the equation v naught times time plus 1/2 the acceleration in the y component times time squared. V naught is 0. So that cancels out all the time. So delta y equals 1/2 the acceleration, which is negative 9.8 meters per second squared, times your time squared. If I'm solving for it at time 1, I'm going to use 1 squared, which is just 1. So after 1 second, it will have fallen down 4.9 meters. Okay. The cannonball is under the influence of gravity alone. So if we just substitute this for the cannonball, it's going to be exactly the same, 4.9 meters. But the cannonball also has an x component. Okay? It's also traveling across. From what they gave us up at the top, it's traveling across at 20 meters per second. So we're going to use the same equation, but now for the horizontal component. Delta x equals v x initial times time plus 1/2 the acceleration in the x component times time squared. There is no acceleration in the x component, okay? So that cancels off. Basically, we have distance equals velocity times time. So delta x equals the velocity, which is 20 meters per second. We'll start at just the first one, 1 second, and it goes 20 meters. So y is 20 meters. And we can use this to track the trajectory. Okay, so at time 1 second, the baseball is 4.9 meters. So that's 10, that's 24.9. Isn't very far. It's probably like right about there. The cannonball has gone over 20 meters in 4.9 seconds. So it's about right there. We'll do the same thing for 2 seconds. And you'll see it get farther and farther away, just tracking the trajectory of the ball. Okay. Let's go ahead and do 2 seconds just to make sure we have this down. So now I'm going to use the same equation. So it's a different problem, but I'm going to use 2 seconds. So 1/2 times negative 9.8 meters per second squared times 2 squared. So I have 1/2 times negative 9.8 times 2 squared, negative 19.6. So it's fallen down 19.6 meters. Okay, that means the cannonball has also fallen down 19.6 meters. Okay, this is the chart for the cannonball. Okay. They're the same. Now the cannonball also traveled across. So it's x, do it over here on the side, delta x equals 20 meters per second times 2 seconds, so 40 meters, okay, which makes sense. It's going to travel the same distance across each second. So we have 19.6 meters and 40 meters. So now at 2 seconds, it's at 19.6, which is basically right at 20. Okay. This one has gone over 40 meters, and it's at 19.6. So right like that. So we can get started tracking that path. Okay. Noting that they're going to be in the same vertical position the whole time. All right. So that's how we can understand the trajectories. Let's try a problem where we're actually having to calculate something. Okay. If you need help on this problem, physicsclassroom.com has great example problems. They're in the student extras, really great practice problems. Since that one's on the website, I'm going to do number 2. It stars me, Miss Peterson, being kicked off a 30-meter high cliff, probably by a grumpy student, at an initial velocity of 4 meters per second. And it wants to know how far away from the cliff I'll land. There's a lake 15 meters away. Hopefully I hit the lake because I don't want to fall into the cliff. So just like any kinematics problem, the first thing we're going to do is we're going to draw it. Okay. So here's the cliff. There's me. Okay. I have a ponytail. And my initial velocity is 4.0 meters per second in that direction. And I'm going to take a path, something like this. This cliff is 30 meters high. Okay, that's how tall the cliff is. And I want to know how far away from the cliff I'm going to land, or my change in the x position. So whenever we do projectile problems, we have to separate it into its horizontal and its, you can do it in a different color, and its vertical components. Okay. Let's start with the horizontal. So the x velocity, the initial x velocity in the horizontal direction is given to us. It's 4.0 meters per second. Okay. In the vertical, I'm not going down at all when I start. So the initial velocity in the vertical direction is 0. There's going to be no acceleration in the horizontal direction. I'm going to be going 4 meters per second the whole entire time. Okay, so the final velocity in the x direction is 4.0 meters per second because there is no horizontal acceleration. In the y direction, gravity is going to accelerate me at negative 9.8 meters per second. And I could use that to solve for my BY final. I don't know it, but I don't really need it at this point, so I'm not going to worry about it. Okay. Last thing we need to know is how far I'm going to fall in the x direction. This is what it's asking us for. I don't know that right now. I do know how far I'm going to fall in the y direction. Do know delta y is going to be 30 meters. Okay? And these two things are unified by time. Okay? Because it's one motion, the time is going to be the same for the horizontal and the vertical. Excuse me. For any of these problems, time is what you're going to want to find first. And we have enough information in the vertical to find time. We don't care how fast I'm going vertically when I hit the water. It's not asked about, we don't care about. So we're just going to ignore that. Okay? So I have my initial vertical velocity, my initial vertical acceleration, and how far I'm going to fall. So the equation that I'm using is delta y equals v initial in the y direction times time plus 1/2 the acceleration in the y direction times time squared. Vy initial is 0, so that term cancels out. Now I can plug in numbers. Remember, always in the y, so 30 meters equals 1/2 the acceleration, negative 9.8 meters per second squared, times time squared. Okay, so we do the math. This comes out to negative 4.9, and then I'll divide it here, so negative 4.9. So I get 30 divided by I get 60.1. The units work out to seconds squared, but it's not important right now. Equals t squared. Take the square root of both sides. And I get that time equals 2.5 seconds. Okay, so time is 2.5 seconds. Now I can use my time to solve for how far across I will go. I'm going to be using the same equation, but now in the x component. So delta x equals v x initial times time plus 1/2 acceleration in the x component times time squared. There is no acceleration in the x component. So I basically have distance equals velocity times time. Okay, one of our basic equations since there's no acceleration. So delta x equals velocity, which is 4.0 meters per second, times the time, 2.5 seconds. And I get 10 meters. Which is very sad because the lake was 15 meters away. So I didn't hit the lake. I hit the ground. And that's not good, but oh well. Okay, so there is your answer.